Alright, so now what we are going to do is we will continue with the proof of the Arzela-Ascoli theorem. Okay, so conversely, suppose that A in CXR, suppose A in CXR, or of course you could have taken CXC. Okay, instead of real valued functions you could have taken complex valued functions, is a closed subset such that A is bounded and equicontinuous. Okay, we will show A is compact. And how will we show that A is compact? We will show A is compact by showing that A is sequentially compact. Okay, because you know compactness is equivalent to sequential compactness for a metric space. So we will show A is compact by demonstrating that it is sequentially compact. Okay, now so what you have to do is that you know we'll pick a sequence from A. Okay, this is a sequence of functions in A, and we'll assume and then we'll try to extract a subsequence which is convergent. That's what sequential compactness means. Sequential compactness means that every sequence admits a convergent subsequence. Okay, so for this we pick any sequence f1, f2, etc. fn, and let me call it as S of A, and show that there is there is an convergent subsequence okay. So we start with any given sequence in A and we try to show that there is a convergent subsequence, but now notice that CXR, okay, the space of continuous bounded real valued functions on X, mind you, is a Banach algebra. It's complete as it's a complete norm linear space with the norm given by the sup norm, okay, the supremum norm. So any closed subspace of a complete space is also complete. Okay, therefore since A is closed, A is also complete. This means that every Cauchy sequence converges. Of course you know that convergent sequences are Cauchy. Okay, so in order to show that there is a convergent subsequence, it is enough to show that there is only a Cauchy subsequence. So finally what we will do is we will use the closedness of A and we use the completeness of the bigger space, the Banach algebra, to reduce to showing just that we will be able to extract a Cauchy subsequence. Okay, so you have to just check that there is a subsequence which satisfies the Cauchy property. Okay, so let me write that down. Since A is closed and CXR is complete, A is complete, so you know we just need to show that S, the sequence S which consists of f1, f2, etc. fn admits a Cauchy subsequence. So, so this is what we have to show, right? And what is it that we are given? We are given that the family A, the collection of functions A, the subset of functions A is equicontinuous and it is bounded. Okay. Now let's analyze what these conditions mean. Okay, and of course we are also given the condition that X is compact. Mind you, X is a compact metric space, so that also needs to be used. Okay, and mind you, because X is a compact metric space, automatically all the continuous functions on X are automatically bounded. Okay, normally if you take a non-compact space, if you look at continuous functions, but if you want to define the supremum norm, you will have to restrict to bounded functions, okay, so that you get a finite norm, all right, for every function. But then in this case you don't have to restrict to bounded functions among continuous functions, because every continuous function is bounded, and that's because X is already compact, right? Now so what I'm going to do is that let's analyze the condition that A is bounded. Okay, we are given A is bounded. What does this mean? This means that there exists an m greater than 0 such that the norm of f is less than m for all f in A. Okay, so basically A is bounded means that A is bounded as a subset of CXR bounded as a metric space. Okay, bounded as a metric space means it is contained in a finite open disk. I mean an open disk of finite radius centered at some point. Okay, but you can choose the point to be the origin, because this is a norm it's not just a metric space, it's a norm linear space, it's actually a vector space. So there is a 0 element, and every vector, every element there, every vector has a norm, and it's the norm that induces the metric, because it's a norm linear space. So saying that a subset is bounded is the same as saying that all the norms, the lengths of the vectors in the subset, they are all bounded by a positive value, and that's what I've written. Okay, so mind you, what does this mean? But what is norm f? But norm f is what? It's supremum over all x small x belonging to capital X mod of x. This is what norm f is. Okay, this is a supremum norm, and this is less than m, and this is true for all f in A. Okay, and what does this mean? This implies that for all f in A and for all x in A, for all x in X, okay, mod fx is less than or equal to m. Sorry, is less than m. I could have used less than or equal to, but probably it doesn't matter. Let me stick to less than or equal to if you want. Doesn't matter. Okay. Now you see, look at this condition. If you look at this condition, now I've rewritten this condition with the points of the domain X of the functions. So if you look at it like this, you see that what you're saying is that for all the functions in A, okay, M is a uniform bound for the function values, and that's why this boundedness as a subspace of CXR is actually uniform boundedness, and that's why this Arzela-Ascoli theorem is called the uniform boundedness principle. Namely, it says that uniform boundedness plus equicontinuity will imply compactness. Okay, that's the other way in which this theorem is often stated. So the uniform boundedness comes from this. So what this tells you is that A is uniformly bounded. Uniformly bounded, and this uniformness is a kind of double uniformness, because it's a uniform bound for all the functions in A, and for each of those functions it's a uniform bound for all points of X. So it's a double uniformness. It's a uniform in the F, it's uniform in the X. Okay, in that sense it's a uniform bound. Okay, so that is one thing that's given to us. Then the other thing is the other thing that's given to us is that this family or this collection A, the subset A of functions is equicontinuous. And what is that? So let me write that down. We are also given that A is equicontinuous, i.e. given epsilon positive, there exists a delta positive such that d, the distance between x and x prime lesser than delta, will imply that the distance between fx and fx prime, which is just the distance function, is just the modulus of the difference of the function values, since these are real values, is less than epsilon for all f in A. So this is the equicontinuity. The equicontinuity is that it's just the same. The equicontinuity for a family is just the same as the epsilon delta definition for a single function, but the only thing is that for a given epsilon, the delta works for all functions, okay, at any given point, okay, and usually the delta will also change as you change the point, but here you can even make the delta independent of the point also, because the functions are all continuous functions on a compact space, and therefore they are uniformly continuous, okay. So so you have this. So this is, so these are things that we are given and we have to use, okay. So the first step of the proof will be let me tell you the idea of the proof. The idea of the proof is that the first thing we will do is that we will show that see, basically we have a sequence, okay. We are given a sequence of functions from A. We have to pick out a Cauchy subsequence, okay. So mind you, saying that this that you have a Cauchy subsequence is means this is Cauchy in the metric for the space of functions, but that means uniformly Cauchy with respect to points of x, okay. See, what you must understand is that whatever you say for functions on with respect to the metric on CXR, okay, that will translate, if you because of the sup norm, if you translate it to an equivalent statement concerning points of x, it will become a uniform statement, okay. It will be a property which doesn't depend on the particular points of x, so it will be uniform on x, okay. So for example, convergence in the space of functions will correspond to uniform convergence on x. Boundedness in the space of functions, as we just now saw corresponds to uniform boundedness, okay. So whatever you say in the space of functions, that will correspond to a property which is uniform with respect to points of x. That's what you have to remember when you translate from function theoretic property to the space theoretic property. The property, you will get a uniform version. It's a uniform version because it doesn't depend on the points of x where you are verifying it, okay. So basically what we have to do is, from the given sequence we have to pick a Cauchy subsequence, but this is a Cauchy subsequence in the with respect to the metric on the space of functions, but that will translate to a uniformly Cauchy sequence of functions with respect to x, okay. That's what we want, right. Now the trick is that what we'll do is that we'll make use of the fact that because x is compact, it's a compact metric space, x is actually separable, that is, it has a countable dense subset, okay. And then what we will do is that we will, using this countable dense subset, we will extract a subsequence, okay, using a diagonal argument from the original sequence of functions, such that this subsequence will converge at all points of this countable dense subset, and then we will use the equicontinuity to show that that is good enough to say that the subsequence is Cauchy on all of x, okay, because it's already uniformly Cauchy on a dense subset, okay. So this is the trick. So the first step that we need is a compact metric space is separable. We need that fact, okay. So let me state that here. Step 1, since X is a compact metric space,
space
X is separable. That is, X has a countable dense subset. And how does one prove this? This is just an exercise saying that a compact metric space is separable. The method is very, very simple. So what you do is basically for each n greater than 1, actually you could have taken any sequence of numbers going to 0, which is any sequence of rational numbers going to 0, but I will choose 1 by n. For each n greater than or equal to 1, look at all the open balls centered at various points of x of capital X of radius 1 by n. Okay. So you take n equal to 1, 2, 3 and so on, and for each fixed value of n, look at all the open balls centered at various points of x, radius equal to that n, at 1 by n, okay, reciprocal of that n, right. So in the first case, I will look at all balls, open balls at various points of x centered at various points of x with radius 1. Then I look at all open balls of x centered at various points of x with radius half, and then I will next look at radius 1 by 3 and so on. Okay. Now each of these for any fixed n, each of these is an open cover, and x being compact admits a finite subcover. Okay. And from that finite subcover you pick the centers, that will give you a finite set of points. So for every n you get a finite set of points, and you put together all these sets of points as n goes to infinity, you will get a countable union of countable sets, and that will serve as the countable dense subset of x that you are looking for. Okay. So let me write that down. This set, this is an open cover of x, hence admits a finite subcover, and we label the finitely many elements, the finitely many points of x which are centers of balls in that finite cover and we label the set of, let me put set of as C sub n. Okay. So Cn is those finitely many points of x such that the open ball centered at those points radius 1 by n covers x. Okay. And you do this for every n. Each Cn is a finite set. Okay. Then union n equal to 1 to infinity Cn is a countable dense subset. Of course it is countable because it is a countable union of finite collection of sets, so it is countable. Okay. And why is it dense? It is dense because give me any point of x and give me any epsilon greater than 0, I can find an n large enough so that 1 by n is less than epsilon. Okay. And then if you that point has to lie in the open cover consisting of balls of radius 1 by n. So it has to be within distance of 1 by n from one of the points of Cn. Okay. And that means that the points of your set, the union of all the Cn's, they come in infinitesimally close to every point of x. That means that their closure is all of x. That is the reason why x is this subset is dense. Okay. Now what we will do is that since it is a countable subset, we will again relabel the points as x1, x2, x3 because it is countable. Okay. So let us label the points of the set of this set as x1, x2 and so on. Okay. Right. So so the step 1 is to get this, you can think of this as some test set of points where you want to test convergence. Okay. So and this test set is just this countable dense subset. Okay. And you know why you need the countability, because you want to be able to extract a subsequence, and extracting a subsequence means you need some algorithm for getting hold of a countable subset. Okay. So you need countability, right. Okay. And now you see, now what we will do is, so this is step 1, we have got this this countable subset of points which is dense. Step 2 is to show that you can extract a subsequence from your original sequence of functions which converges at all of these points, converges pointwise at each of these points. Okay. Now that is done by a standard trick which is called a diagonal argument. Okay. So the idea is very, very simple. The idea is, see, I have already a sequence of functions f1, f2, f3 which I call as S. Now what you do, and I have this sequence of functions on the one hand, on the other hand I have this sequence of points. I have this sequence of points x1, x2 etc., which is a countable dense subset of your metric space, compact metric space. Okay. What I do is I test point by point. I first take this point x1, I substitute in these functions, so I get f1 of x1, f2 of x2, f2 of x1, f3 of x1, I get this. I substitute the point in the function, in the set of functions, and what am I going to get? I am going to get a bounded sequence of real numbers. Why is it bounded? Because I know that all these functions are all uniformly bounded. So there is a bounded sequence of real numbers, and you know a bounded sequence of real numbers has to admit a convergent subsequence. So there is a certain convergent subsequence of functions. There is a subsequence of functions which converges at x1. I will extract that sequence. Then what I will do is I will repeat the process with x2 for that subsequence of functions. So from that subsequence of functions I will get another subsequence of functions which will converge at x2. Okay, and then I will repeat this process ad infinitum. So what will happen is at the nth stage I would have extracted an at the nth level I would have extracted a subsequence of a subsequence of a subsequence at the nth level, okay, which converges at xn. And if I do this ad infinitum, okay, the point is that you take you write the functions in each stage in the form of a row, okay, and you have you write it as rows, and then you get countably many rows, and then you take all the functions in the diagonal. The point with all the functions, taking the sequence of functions in the diagonal is, of course you will get a countable subsequence, but the point is that this sequence will converge at all points of the dense subset, because at some stage if you take all the functions in the diagonal, the ith functions will converge at it will converge at x1, x2, x3 etc. up to xi, okay. And then what will happen is that if you keep letting I become larger and larger, you will see that all the functions converge at all points of this countable dense subset, okay, and that is the critical step. So let me write that down. So step 2, we extract a countable, that countable means a subsequence S, subsequence of S which converges pointwise at each xi. Okay. that is it converges pointwise on that countable dense set. How do you do that? So let me do it figuratively. So you have S is equal to F1, F2 and so on. Okay. What you do is, well, substitute x1, what you will get is you will get F1 x1, F2 x1, F3 x1 and so on. Okay. And note that mod Fj x1 is less than or equal to m, because this m is a uniform bound for all functions of A, and after all the sequence S has been taken from A. Okay. So, but this is a bounded sequence of real numbers. Okay. And you know, if we were working with complex functions, you would have got a bounded sequence of complex numbers. Any bounded sequence of real numbers or complex numbers does admit a convergent subsequence. Okay. So, so let me write this here. This admits a convergent subsequence. So what you will get is you will write you see you get a convergent subsequence of real numbers, okay, or complex numbers, whatever it is. Okay, depending on whether we are now looking at real valued functions. If it were complex valued functions, you will get a convergent subsequence of complex numbers. But then forget now the numbers and look at the functions that have come up. Okay, forget the x1 and look at the f's. So what let's call that as f11, because I want to use this, I am relabeling that. So f12, f13 and so on. Okay, mind you, this is subsequence of S. Okay, and I am relabeling. In principle, I should write as f if you want. Well, you know, I could use different methods of relabeling, but let me use this. Okay, so these Fij's, F1j's are just these the first subsequence I picked out from this set. Okay, now what I do is I repeat the same process for this S1 with x2. Okay. And I proceed. So let me write that once more. So do this, you substitute x2, then what you will get is you will get this f11 x2, f12 x2 and so on, and again you will have mod f1j x2 is certainly less than or equal to m, because it is a uniform bound, it works for all functions and for all points. Again, this admits a convergent subsequence, this admits a convergent subsequence. Okay, and again now what you do is you relabel the subsequences f21, f22. So I will get s2 which is now f21, f22, f23 and so on. Now this is a subsequence of S1, which in turn is a subsequence of S. Okay, but the point is that this S1, this converges at x1. When you plug in x1, this converges at, what about this? This converges both at x2 and x1, because it is already a subsequence of S1. So this converges at x1 comma x2. Okay, and then now you proceed by induction. What you get is you will get Sn, which will consist of functions fn1, fn2, etc. This is a subsequence of Sn minus 1, which in turn is a subsequence of S, and this will converge at x1 dot 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 up to xn. Okay, and you can do this for every n. All right. Now what you do is you write down all these Fij's as an array and pick the diagonal sequence. That's the sequence that we are looking for. That's the sequence that will converge at all points, at all these points of this countable dense subset, and that's the sequence that is going to be a Cauchy sequence, as we will see. Okay, so write all the functions, all the Si in rows, So here is S1, this is F1, 1, F1, 2, F1, 3, F1, 4 and so on. There is S2, there is F2, 1, F2, 2, F2, 3, 4 and so on. And it goes on like this, and if you write Sn, I am going to get Fn1, I am going to get Fnn, okay. And of course, and well, this is how it is, and there are commas in between if you want, but anyway, okay. Now what we are worried about is the diagonal subsequence. So we are worried about this guy. Pick this. Put G1 is equal to F11, G2 is equal to F22, and so on, Gn equal to Fnn, and so on. Okay. Then the claim is that, of course, this G1, G2, there is a subsequence of the original sequence S. Mind you, this S2 is contained in S1, S3 is contained in S2, Sn is contained in Sn minus 1, and all this is contained in S, which was the original sequence, which consisted of F1, etc., Fn and so on. Okay. So what you get is you get this sequence G of Gj's. These Gj's are all a subsequence of the original S, but the beautiful thing with this Gj is that these Gj's will all converge pointwise at every point of X. Okay. So in fact, at every point of that countable dense subset. Okay. So then so let me write it here. Then Gj is a subsequence of S. Gj converges at each xi. And why is that true? Because if you give me an xi, then from gi onwards, okay, all gi plus 1, etc., they will all converge at xi. Okay, all right, because gi xi, gi plus 1 xi converges. Okay. See, for a sequence to converge at a point, it's enough if beyond a certain stage all the members of the sequence converges. So if I want to check the gi, if I want to check gi when I substitute, when I take the sequence gj and substitute xi, if I want to say gj of xi converges, it's enough to show that gj of xi converges beyond a certain j. And what is that j? That j is from I onwards. Okay, that's what I'm saying. Okay, so this is this is a diagonal trick which is very cleverly used. Okay, so we have this. Now we are now the claim is that Gj converges in fact I should say let me say Gj is the required Cauchy subsequence of S. Okay, so this is the claim. This is the claim. Okay, so finally we are able to extract a Cauchy subsequence, and that's good enough, right? Now how do you check its Cauchy? You have to check its uniformly Cauchy. Okay, because its Cauchy in the space of functions means that it is uniformly Cauchy with respect to points of X. Okay, so you have to bring in points of X somehow. All right, and the point is that we'll have to use what we have not used so far. We have already used the closedness of A, because we have reduced from finding a convergent subsequence to a Cauchy subsequence, okay, and we have used the closeness to use the fact that A is already complete, okay, a closed subspace of a complete space is complete. We have not used the equicontinuity, we have to use the equicontinuity, okay, and what you will have to do is that you will have to use the equicontinuity of this family A. In particular, it also applies to the functions in the subsequence Gj, because after all they are all functions from the same family A, okay, this collection A. We have to use the equicontinuity, and but then the thing is that we will also have to use the see we will have to use the compactness of A again. See, that's because first of all what we have proved is that we have got a, because of the diagonal argument, you have gotten hold of a subsequence that converges at all points of a countable dense subset, okay, but from that you want to conclude that it converges at all points, okay. First of all you have to conclude that it converges at all points. You have to conclude that using the information that it converges only on points of a countable dense subset, okay, and for that how do you reach an arbitrary point from this given dense point? There you will have to use compactness, okay, and there you will have to use equicontinuity. So what we will do is that so let me write out. So this is the final step more or less. So this is, well, let me put this as so what I had called it as step 2 maybe. So this is step 3 actually. I have to show that this is the required Cauchy subsequence. So what you will do is that so let epsilon greater than 0 be given, okay. What do we have to show? We need to show there exists an n such that m comma n greater than or equal to n implies mod gj gm. So this is the Cauchy condition. So I should say distance. So let me write, so norm gn minus gm can be made less than epsilon. This is the Cauchy condition. Mind you, this is the norm gn minus gm is the distance between gn and gm in the metric induced by the norm in the space of functions, okay. I have to show that this can be made less than epsilon for if the subscript of the sequence goes beyond a certain stage, okay, that points of the sequence come to within an epsilon beyond a certain stage. That is the Cauchy condition, okay. But of course this norm is a sup norm. What this means is that is for all x belonging to x, you must show that mod gn of x minus gm of x can be made less than epsilon, okay, and you see the important thing is that here you see this is because the norm is a sup norm, alright. So we will have to show this. So how do you do it? Mind you, the x is an arbitrary point of x, so you have to tackle an arbitrary point of x. So what you do is so at some point, you know, you have to reach an arbitrary point of x from one of the points in the countable set, okay. But then this is but there are too many points in the countable set, there are countably many, but you have to reduce to finitely many. So this is where you again use compactness of x, okay. So what you do is you look at a cover of x by open balls of radius delta, okay, where you see where that delta is this delta that we already have for the equicontinuity. So where is it? It's here. So there is this delta here. If you go back, A is equicontinuous. So given epsilon greater than 0, there is a delta such that whenever the distance between x and x prime in x is delta less than delta, then mod fx minus mod fx prime is less than epsilon, okay. We have to use that delta, but then you see, since we are going to interpolate with points from a finite subset of points, the distance in the triangle inequality will be broken into 3 terms. So we will take this delta corresponding to epsilon by 3, okay. So what we will do is, so let me write that down, let delta greater than 0 be such that whenever the distance between x and x prime is less than delta, the distance between fx and fx prime is less than epsilon by 3 for all f in A. This is where we are using the equicontinuity, okay, by equicontinuity. So you started with an epsilon, but you consider epsilon by 3, and then for that epsilon by 3 you pick a delta. Now use this delta to form and look at this open cover which is formed by open balls of radius delta. That will have a finite subcover because x is compact, okay, and take those points, those finitely many points, okay, and use those points to interpolate between fx and fx prime using the gj's, and you will get what you want. Okay, so that is the idea. So look at the open cover of x centered at various points of x. In fact, I would like those points to be one of the points in the countable collection. So instead of taking all points of x, I will even take the points from this countable dense subset. Even that will form an open cover because the subset is dense. Okay, so look at the open cover of x centered at points. So not all points, at the points x1, x2, etc. of x. Okay, so I could have taken all points of x, but I am purposely taking the points of the countable dense subset. Okay, that will also form an open cover because their closure is all of x. Okay, since x is compact, this admits a finite subcover so say with centers xi1, so you will get a subsequence of the xi's, so you will get x, which I am calling as xi1, xi2, etc., xim. Okay, my I looks like j. Not able to write I. Okay. Mind you, these xi's are finitely among those points which form a countable dense subset. Okay, and now what you do is that you see now the trick is that I will have to interpolate mod fx minus fx prime with these xij's and the gj's. Okay, and get what I want. All right.